So this is section 5.5 on bases other than E. So the log properties that we covered in section 5.1, I mentioned back then, but I'll just reiterate here that it does hold for logs of any base. Now I say any base, it's actually any positive base other than 1. The reason it can't be 1 is if you have like log base 1 of something equals something else, you wouldn't get unique answers because 1 to any power is always going to be 1. So for instance, one of the properties that we had in 5.1 was the natural log of a times b can expand into the natural log of a plus natural log of b. So if I extend that to another base other than, base e, that would be written log base m of a times b equals log base m of a plus log base m of b. So this is the specific formula for base e, or natural log, and this is the generic formula for just any other base. All right, let's talk about some exponent properties because we're going to need these. We know that any non-zero number to the 0 power is 1. We have these exponent properties that when you multiply with the same base, you add the exponents. When you divide with the same base, you subtract the exponents. A negative exponent can be rewritten as 1 over that same base to a positive power. And if you have a power raised to a power, you multiply those exponents. So we are going to make use of some of those exponent rules along the way. So I just wanted to kind of refresh your memory on those. Okay, so our first derivative formula for this section is the derivative of a to the u. So the derivative of a to the u is the formula natural log a times a to the u, and then we got the chain rule happening here, times du dx. Now, we've already did this in section 5.4 for e to the u, and we did that one, specifically because, we did the natural log stuff first, and then we extended it to other bases. So here we've got the derivative of e to the x, now we extend it to other bases. I am going to derive this for you, and it does come from, kind of a similar thing to the derivative of e to the x. So that means, for example, if I were going to take the derivative of 4 to the x, by using this formula, that would be the natural log of 4 times 4 to the x times the derivative of x. And the derivative of x with respect to x is just 1. So let's look at where this derivative comes from. So you could say this is a derivation of the formula, or you can say that it is a proof of the formula, whichever way you want to look at it. So we first have to do something kind of crazy. We're going to rewrite a to the x as e to the ln a to the x power. Those are the same thing. So remember back in section 5.1, we talked about how e and ln were inverse functions. So e to the ln of something is just that thing. Just like the natural log of e to something is just that thing. The e and the ln are inverses. They undo each other. So this is just a much more complicated way of writing a, but we kind of need that. So I'll show you why. So if I rewrite a as this much more complicated way, then the derivative of a to the x can be rewritten as the derivative of e to the ln a to the x. Now from our exponent rules, we know that having a power raised to a power, we multiply those exponents. So I'm going to multiply ln a times x. Now notice how I wrote it x times ln a. I did that because I don't like writing ln a times x, because then you have to wonder, is that x part of that log argument or not? So just to avoid that confusion, I bring that x out in front so that you know for sure, hey, that a and that x cannot be multiplied because a is part of the argument of log, x is not. So now the derivative of e to the x ln a. Here, we just need to use our derivative formula from the previous section that says the derivative of e to the u is e to the u du dx. So the derivative of e to something is just e to that thing times the derivative of that thing. Well, the derivative of x ln a is just ln a, because ln a is just a constant. So it's just like saying the derivative of 3x is just 3. Same thing here. It just happens to be that we don't have a nice number like 3. We have ln a as a constant. Now remember that e to the x ln a is the same thing as a to the x. So I can rewrite this as this. So I had to kind of temporarily write it in this, kind of more complicated version, just to be able to utilize my formula for e to the u and then bring it back to this a to the x business. All right, so next up we have the derivative formula for log base a of u. So that derivative is 1 over u times ln a times du dx. So I just gave you an example of how that would be used. So if we had log base 5 of 3x and we're going to take the derivative of that, then this would be 5 is my a and 3x is my u. So 1 over u ln a times du dx. So that's the derivative of 3x with respect to x. So that would be 1 over 3x ln 5 times the derivative of 3x. And those 3's can just cancel off, and we just get 1 over x ln 5. So just want to kind of show you immediately right after the formula how it would work with something a little more normal and a little less lettery. All right, so let's derive this formula as well. First, we're going to need something called a change of base formula. You might remember this from college algebra, or it might have been a hot minute since you've seen it before. But the change of base formula says that you can take, if you have like log base a of x, you can rewrite it with any log, so any other base. I chose ln for this one because we know how to take the derivative of ln. Just like the last one, I changed it to e because we know how to handle e from the previous section. So this would be ln x over ln a, where this x and this a are the same as this x and this a. And of course, a has to be positive because you can't take the log of a negative number or 0. All right, so that means the derivative of log base a of x is now rewritten as the derivative of ln x over ln a, just from that change of base formula. Now remember, ln a is a constant. So that means when it comes to taking the derivative of this, I can take this 1 over ln a out because it's just a constant. We know that when you take the derivative of a constant times a function, that you can take that constant out and just make it constant times derivative of the function. So that's all I did, was pull that 1 over ln a out. Now the derivative of ln x, we know is just 1 over x. So we get that formula of the derivative of log base a of x is 1 over x ln a. All right, so let's look at some examples. So starting off with y equals 2 to the 3x, we want to find the derivative. This is a to the u. All right, so my derivative formula for a to the u is ln a times a to the u times du dx. So a is 2, u is 3x. So that's going to be ln 2, so ln a to the u, and then the derivative of u, so the derivative of 3x is just 3. I can rewrite that a little bit nicer. I just put 3 ln 2 times 2 to the 3x. I mean, you could have just left it like that and that would be fine. Don't get crazy on me and start doing crazy, just like crazy crackhead level stuff here. Don't be like, oh, I'm going to multiply that and get 6. Oof, don't do that. You can't multiply those. Okay, let's look at another one. All right, so part B Okay, part B here is y equals 5 to the 6x quantity squared. We can first use the exponent rule to multiply those powers. That'll give me 5 to the 12x. Again, this is a to the u, where a is 5 and u is 12x. So the derivative is going to be ln 5 times 5 to the 12x times the derivative of 12x. And if I just want to clean it up a little bit, there it is. But it'd be perfectly fine if you just left it just like that. So pretty easy peasy, right? So with this one's a little bit weird because I had to use the exponent rule first, because otherwise you'd have to use the chain rule, and not necessary. All right, so let's look at this one. This one we're going to need the product rule as well as that derivative of a to the u business. So let's get a little fuzzy on me. All right, so if we use the product rule, we have the first times the derivative of the second. So the derivative of sine 3x, we need the chain rule. Derivative of sine is cosine, and then the derivative of 3x is 3. So it's first times the derivative of the second plus the second times the derivative of the first. So all this is the derivative of this a to the u. Okay, so this a to the u is going to be ln a, so ln 5, times a to the u, 5 to the 7x, times the derivative of 7x. And we're just going to leave it like that. We're not going to try to clean that up. There's not really much else that we can do with it. All right, so let's do a log problem then. With this one, let's use the log properties to split this up, okay, before we take the derivative. So first thing I did was a subtraction because of this division right here. So I did log base 3 of the top minus log base 3 of the bottom. And then right here, this is multiplication, so I can split that apart with addition. I can do one more log property. That's because this square root we know is the same thing as a 1/2 power. And we know if there's an exponent on here, we can bring that 1/2 power out in front. But be careful, just in front of this term. Don't bring it all the way out in front of there. It's just in front of this term. So that's what it looks like after I've used the log properties. Now look, notice this says f of x. I have not taken a derivative yet. All right, this is the same function as I started with. All right, now I'm taking a derivative. So now you can see that I have f prime of x in there. All right, so to start with, I've got log base 3 of x. That derivative is going to be 1 over x ln 3. This 1/2 is just a constant multiple. Then the derivative here is going to be 1 over x minus 1 times ln 3. And then this derivative is just going to be 0 because this is just a constant. Now, how do you know that's a constant? Do you see a letter? Do you see a variable? No? Then it's not varying. It must be constant. So that constant is just going to be 0. So for this one, I used this derivative formula. So when I got to this point right here, just in case you're wondering how I got that, that's the formula that I used in there. All right, so let's use a technique that we did. Oh, when did we do this one? Maybe section 5.1, logarithmic differentiation. That's where you bring in a logarithm. That's where it's like, okay, there's not a logarithm in here, but wow, it sure would be easier if we brought one in. So let's bring a logarithm in. So let's take the natural log of both sides of this equation. The benefit from doing that is that this exponent up here that's, that's totally being weird on us now gets to come out in front and become that. Now this is a lot nicer to have to differentiate because now we're just talking product rule. All right, so we differentiate both sides. Over here, we're going to have to use implicit differentiation because we're differentiating both sides with respect to x. So this is going to be the derivative of natural log y is 1 over y, and then by the chain rule is going to be dy dx. Over here, I'm going to need the product rule. So it's the first times the derivative of the natural log plus the natural log times the derivative of x minus 1. So all of that came from the product rule. To solve this for dy dx, I'm going to need to multiply both sides by y. So I get dy dx equals this stuff over here. I just cleaned it up a little bit. Like right here, x minus 1 over x. And then ln x times 1 is just ln x. And then here's multiplying both sides by y. I multiplied this side by y, and when I did that, those y's went away. And then I'm going to replace y with x to the x minus 1. And I'm done. I'm not sure there's another way to do this without using logarithmic differentiation here for this one. Some of them you can kind of just brute force through, but this isn't one of those. Okay, so we have our derivative formula for a to the u, was ln a times a to the u du dx. Because ln a is a constant, we can divide both sides of this equation by ln a. And we get 1 over ln a d dx of the derivative with respect to x of a to the u equals a to the u du dx. So all I did was divide this side by ln a, get rid of it, bring 1 over ln a to the other side. If I integrate both sides with respect to x, so that's what that little abbreviation means. I don't know if that's a common thing in Calc 1 or if that's just something I use, that abbreviation I use a ton in Calc 1. So if I integrate both sides with respect to x, so if I integrate all this dx, and then I integrate all this dx, then this cleans up. The integral of that derivative undo each other, and I get 1 over ln a of a to the u. Over here, those dx's kind of cancel, and I get the integral of a to the u du. So here, this integral with respect to x and this derivative with respect to x sort of cancel each other out, and I'm just left with 1 over ln a and a to the u. So really what I'm showing you is how I'm able to get this integration formula from the derivative formula that we have. So we get this integration formula that the integral of a to the u du is 1 over ln a times a to the u plus c. You could combine these if you wanted to and just write it as a to the u over ln a. All right, let's evaluate some integrals. So the integral of 6 to the x. This is a very straightforward integral. This is just straightforward. This is the integral of a to the u. So it's just the formula here. 1 over ln a, where my a is 6, times a to the u plus c. And like I said, you can combine these into just one fraction. Just make it a little bit prettier. Of course, we like examples like this that are quick and painless. 5 to the negative x is going to require just a little bit of substitution. We're going to have to let u be negative x, and then du is negative dx. We have an extra negative, so I divided both sides by that negative. So that when I make this substitution, I get 5 to the u, but then this dx gets replaced with negative du. So this negative right here is where this negative came from. And then I replaced negative x with u. All right, so now I've got a to the u, and then I've just got this constant out there. It's just along for the ride. So the integral here of this a to the u, there's that negative along for the ride. It's just 1 over ln a times a to the u plus c. I'm going to substitute back in for u. You don't want to forget that. I'm going to substitute negative x, because that's what I let u equal. And so that'll be negative right here, 5 to the negative x over ln 5 plus c. It's really up to you. If you're more comfortable having these split apart into two things, you can. If you're more comfortable having those together, that's cool too. I'm not picky. All right. Now let's do some more substitution. So the last couple of ones for this section. All right, so I'm going to let u be this exponent up here, this 3 minus x quantity squared. So if I let u be that, the derivative of this, I'm going to need the chain rule for that derivative. It's going to be 2 this to the first power, because I'm going to have to differentiate that squared. Then I'm going to have to differentiate inside the parentheses. So that'll be 0 minus 1, which is just negative 1. So I can combine that negative 1 times 2 and get negative 2 times that 3 minus x. So I'm really close. I got the 3 minus x dx business. I just have this extra negative 2. I'm going to divide both sides by that negative 2 so that I can replace this 3 minus x dx with negative 1/2 du. All right, so making that substitution gives me a much nicer integral of just 7 to the u du with this constant hanging out there, just kind of along for the ride like some mooch. Integrating this a to the u, so here's my negative 1/2 along for the ride. Integrating that's going to be 1 over ln a, in this case a is 7, times a to the u plus c. Substitute back in for u. We get this negative. I went ahead and just combined all this stuff on the top. 7 to the u, which was 3 minus x quantity squared, over 2 ln 7 plus c. All right, last one. We've done a bunch of indefinite integrals, so let's do a definite integral. So this one's the integral from 1 to the square root of 2 of x times 2 to the x squared power. So let's let u be x squared, and then that derivative is going to be 2x dx. I've got an extra 2 over here, so I'm going to divide both sides by 2. That way this x dx gets replaced with 1/2 du. All right, so I get a substitution of this 1/2 and then 2 to the u du. All right, so I'm just going to integrate this a to the u, and this 1/2 is just along for the ride. Integrating this a to the u, I get 1 over ln a, in this case a is 2, times a to the u. I just went ahead and kind of cleaned those up and substituted back in for u at the same time. So be careful, from here to here I did two things at once. I put x squared back in for u, and I just combined all the numerators and all the denominators. So I got 2 to the u on top and then 2 ln 2 on the bottom. So once I do that, now I've got some bounds I need to contend with. So I'm going to plug in the square root of 2 for x, and then I'm going to plug in 1 for x, and I'm going to subtract those. Scooch this up a little bit. All right, so if I plug in root 2 for x, the square root of 2 squared is just 2. So this is really just 2 squared. I know there's a ton of 2's happening in here. This is 2 to the 1 squared. So this is going to be 2 to the second, or 4, minus 2 to the first, which is 2. These have the same denominator, so I can combine those together over the same denominator. 4 minus 2 is 2. I can clean up that numerator a little bit, and then those 2's cancel, and I'm just left with 1 over ln 2 for that one. All right, so that finishes up section 5.5.